Hi and Assalamualaikum Dr. Faiza. So this video is for the project which is task 11 entitled Absorption Analysis through Experimental and Kinetic Study for the Removal of Metallic Ions or Residual from Palm Oil Mill Effluent, which is POME, and prepared by Nurul Maisarah Vanida, Nur Syuhada, Umi Fatihah, and me, Nur Amira Syafiqah. So the objective of this project is to investigate the capability and effectiveness of an absorbent for the removals of residual oil and selected heavy metal ions from POME in batch mode. Second, to study metallic ion and residual oil removal efficiency of adsorbent in continuous mode. And third, to evaluate the effect of various operational parameters and optimal conditions, which include pH and so on. And the last objective is to study isotherm, equilibrium, and kinetic of the residue oil and heavy metal absorption process. As the introductions, palm oil mill effluent is produced annually in huge amount of wastewater by palm oil processing, which is the major oil industry in Malaysia. Annually, 16.3 million ton productions of palm oil in Malaysia and approximately 3 tons of POME is generated for each ton of crude palm oil. POME is a colloidal suspension containing 65 until 66% of water, 0.6 to 0.7% oil and grease, and around 5% total solids. It is thick, brown, liquid with a discharge temperature of between 80 degrees Celsius and 90 degrees Celsius and very acidic with a pH value in the range of 4 to 5. Absorption using zeolite in batch mode, absorptions being the method of choice because it is environmental friendly and low cost method that requires simple technology. Zeolite is defined as a microporous alumina silicate mineral commonly used as a commercial adsorbent and catalyst. The Slovakian zeolite used in that study has higher zinc absorption percentage compared to the majority of tested zeolite before this. However, ferrum removal percentage of all studied zeolites are almost in the same range, that is less than 70%. In case of mangan ion, the zeolite used in that study shows the higher removal ability than the zeolite from Turkey, while Brazilian zeolite remove mangan ions more effectively. For the overall, the absorption process is one of the effective methods for pollutants removal from the waste effluent, especially the heavy metal ions, which include ferrum, mangan, and zinc. It also remove color, odor, and organic pollutant that is we call as undesired product. The process of absorption has an edge over the other methods due to its large free clean operations and low capital intensive nature. Even though zeolite has less absorption capacity toward reducing COD concentrations, the abilities should not be overlooked.
So, Assalamualaikum Doctor. My name is Nashwada Bidinudin and my mentor number is 189873. So, I will proceed on the second question for our project, which is task 11. And the question is to study the metallic ion and residual oil removal efficiency of absorbent in a continuous mode. In this case, we use natural zeolite fixed bed column to study the metallic ion and residual oil efficiency from POME. So the method that take account in this study were prepare the sorbent, wastewater, chemical, experimental setup, analytical technique, effect of operating variable, calculation of experimental parameter of breakthrough curve, theory of model for fixed bed column studies, and lastly is the error analysis. This is the diagram. This is the schematic diagram of the column setup, which is the column packed with the zeolite. This is what will be used. And next is effect of operating variable. We have choose two effect, which is effect of flow rate and also effect of bed height. So the flow rate, we have choose 3 different flow rate, which is 3, 5 and 8 milliliter per minute was used. For each experiment, the bed height column was constant at 10 centimeter and the pH values of formula were adjusted to 3 and 6 for metal and oil removal respectively. This pH was obtained as the optimal value over the batch sorption experiment in our previous work. So at regular interval, the pH adjusted formula was pumped through the fixed bed of natural zeolite and sample of formula leaving the column was collected and analyzed. About 600 minutes, this experiment was conducted. The selection of flow rates and bed height carried out by considering the previously documented research about application of natural zeolite for column adsorption. Next is the effect of bed height. So we have make 3 different bed height. The column was packed with 5, 10 and 15 centimeter of natural zeolite, and the experiment was performed for approximately 600 minutes. Same goes with the effect of flow rate with constant flow rate of 3 milliliter per minute and the fixed value of pH that previously discussed. So we goes with the effect of flow rate. By increasing the flow rate 3 to 8, we can see the breakthrough time decrease from 250 to 70, which is 250 to 50, 150 to 30, and lastly 200 to 50 for ferrum, manganese, and also zinc, and the residual oil respectively. This tendency can be attributed to that at the higher flow rate, the contact time inside the column decreased. Therefore, the solution distributes and diffuse weakly among the sorbent particles that cause the required time to reach the saturation quicker and so result in lower removal efficiency. So we can see this is the graph, the back-through curve based on the BDST and Adam-Boehm model at different back deep. For A is for ferrum, B is for manganese, and this C is for zinc, and lastly D is residual oil. You can see that the graph is increased when we change the flow rate. And this is table 3, column adsorption capacity at various operating conditions at 50% breakthrough concentration. You can see here. So for the effect of bed height, we can see that when we increase the bed height from 5 to 15 centimeter, the breakthrough time increased from 100 to 400, 150 to 450, and 50 to 350 minutes for ferrum, manganese, zinc, and 100 to 250 for residual oil, respectively. It can be observed from figure 3 that represent the obtained breakthrough curve for absorption of metallic ion and residual oil onto natural zeolite at different bed height. This is the graph. This is the picture of the breakthrough curve based on the BDST and Adam-Boehm model. You can see it was increased when we increased the bed height. Not only that, the adsorption capacity will be higher because of higher contact time and higher adsorbent surface area. Therefore, at any time, the ratio C2 over C1 decrease by increasing the bed depth. This trend is expected and has been reported in the other research. So, for the last part is the conclusion. As a conclusion, for the study show that the effect of bed height and flow rate on uptake of heavy metal and residual oil by the natural zeolite for both group of the sorbents, it was found that the maximum uptake occur in the lower flow rate and higher depth of zeolite. Therefore, the flow rate of 3 milliliter per minute and bed height of 15 cm was selected as optimum condition. Optimal condition for column absorption capacity for these three and residual oil were found as 1.455, 0.229, 0.0198 and 100 mg per gram respectively. All the opt-in data were fitted well from breakthrough curve of both experiments in Bohart Adam and BDST model. Finally, it is suggested that natural zeolite is a promising absorbent that could possibly be applied for the removal of both residual oil and metallic ion from the pomade. So that's all from me. Thank you.
Okay, so the next objective is to evaluate the effect of various operational parameters and optimal condition. So this is the operational parameters that I will cover. So firstly, for the effect of pH, the absorption of residual oil by zeolite is significantly affected by the pH because of the surface properties and binding sites present on the surface of absorbent. The pH also affects the emulsion stability by controlling the degree of ionization of residual oil. A study is made and it was found that the removal percentage is higher in acidic condition rather in basic condition, but it is the lowest in neutral condition. This is due to the demulsifying effect of a strong pH, which enhance the absorption of oil. So we can conclude that the optimum pH condition is at pH 3. So the second one is the serum rate. A study is made by using different agitation speed which range from 90 to 200 rpm. So we can see at the figure here that the agitation speed of 200 rpm has the highest rate of absorption. This might due to the thickness of boundary layer surrounding the zeolite particles starts to decrease as agitation speed increase. That leads to an enhancement in the coefficient of film transfer and rate of absorption. The other agitation speed are also increased, but only in small amount. However, when considering the economic aspect of applying a high agitation speed on large scale would be very costly. Also, the close result obtained for 120 and 200 rpm, the agitation speed of 120 and greater is considered as the optimal for the absorption of residual oil. Okay, for the dose of absorbent, different dose of zeolite absorbent also can trigger the residual oil removal process. A study shows that the efficiency of removal will increase as the mass of absorbent increase. When the mass of zeolite increase, this will introduce more binding sites and surface area, which will increase the removal of residual oil. However, too much dosage of zeolite will make the removal remaining constant due to saturation of binding sites. So the optimal dosage will depend on the amount of residual oil itself. Okay, next, the contact time also should be considered when conducting the absorption process. So we can see from figure here, by increasing the contact time, the amount of oil absorbed increase until the absorption reach equilibrium, which is at 50 minutes. We can see that the absorption starts to slower after the initial period due to slower diffusion of oil molecules into the interior channels of zeolite. So we can conclude that the first 10 minutes of the absorption is the optimal condition for the process. Okay, lastly is the effect of initial concentration of oil. So from the figure here, we can see that by increasing the concentration of oil, from 1.6 gram to 8 gram per 500 ml, the absorption capacity increased. This may due to high mass driving force generated by the initial oil concentration that overcame the mass transfer resistance of all molecules between aqueous solution and solid phase. So we can conclude that the optimum absorption is at the concentration of 8 gram per 500 ml because it has the highest absorption capacity. So that's all from me.
My name is Nurul Maisara. I'm going to explain about the studies about isotope, equilibrium, and kinetic of the residue oil and heavy metal absorption process. Okay, isotope. What is isotope? Isotope is used to describe the interaction between the metal ions and the solvent. For example, that I take from the Journal of the Chemical Engineering Taiwan. Equilibrium study were performed by adding and accurately weigh 25 grams of natural zeolite to 250 beakers containing different initial metal ion concentration. For POME was considered 100%. The suspension was shaken at the 120 at room temperature at equilibrium at 180 minutes. For absorption isotopes, two most common namely is the Lemieux and the Freundlich. Okay, for the linear form for Lemieux model is this formula. So CE, what is CE? CE is the concentration at equilibrium. Q is the metal ion absorbed at equilibrium. QM is the capacity of the monolayer absorption at equilibrium. And KL is the Lamier constant. Okay, next, this graph for the Lamier absorption isotope for ferrous, zinc, and manganese ions. And this is a Freundlich absorption for that ion. Here we can see the difference between these two types. The graph is a very difference. Okay. For example, for figure A, from this graph, CE over QE versus CE. From this graph, we can find the intercept value of 1 over QMKL and the slope of 1 over QM from this graph. Okay, next is the essential characteristic of the Lamier isotope equation in terms of dimensional equilibrium constant. Okay, this is the formula, and RL is the indicate the types of isotope to be either irreversible, variable, or linear. Okay, this is the Freundlich equation. Okay, this is a table result that obtained for the Lamier and Freundlich model for the removal metal ion. Okay, for the correlation coefficient R2, we can see that for Lamier isotope model, the value is highest than the Freundlich isotope model. You can see that for the Lamier, 0.998, 0.999, and 0.998 for ferrous, zinc, and manganese respectively, compared to the Freundlich isotope model. We can see that Lamier isotope model, the value is more higher than the Freundlich model. Okay, this is the graph of experimental data fit into Lamier and the Freundlich isotope for ferrous, zinc, and manganese. Okay, next I will talk about kinetic of residue oil and heavy metal absorption process. There are a lot of mechanisms such as particle diffusion, mass transfer, and chemical reaction control the process absorption. The kinetic data of the ferrous, manganese, and zinc was evaluated using the pseudo-first order, pseudo-second order, and intra-particle kinetic. So, I will explain about the pseudo-first order and pseudo-second order. This is a formula of pseudo-first order and the pseudo-second order. This is for pseudo-second order. Okay, the QE is the absorption capacity at the equilibrium, and the QT is the absorption capacity at time. K1 is the rate constant for pseudo first order, and K2 is the rate constant for the pseudo second order. Okay, this is a graph and using the pseudo first order, and this is a graph for using pseudo second order. Okay, next about the equilibrium of the residue oil and heavy metal absorption process. Absorption equilibrium study were conducted using the optimum conditions. Absorption equilibrium was determined at different initial concentration of residue oil with the optimum condition. In the technological application, the absorption process is generally a part of a continuous process, and the processes are usually conducted under the steady state condition. For very high absorption rates, the steady state could be viewed as an equilibrium state, but in most cases, the steady state remains far apart from the equilibrium. For this reason, together with the Lamier equilibrium parameter of an absorption system is essential for describing precisely the performance of an absorption unit operating in technological process. That's all from me. Thank you.